YouTube. In this video, we're going to be discussing how you take a complex number and easily raise it to a power. And this is conveniently done using what we call DeMoivre's theorem. Okay, so DeMoivre's theorem, basically the primary stipulation is this. Your complex number has to be written in trig form. However, if it is written in trig form, this RCIS theta form, then DeMoivre, what he said was this: as long as n is an integer, then z to the nth power would have to be equal to our complex number, which is this RCIS theta thing, also to the nth power. But according to this property here, what it says is this: we would take our RCIS theta to the n, and we would take our modulus to the nth power, and then as far as what we do with the arguments, we're just going to take our arguments times that whatever that power is up here. Okay, so really, if we had to boil this down to kind of its nitty-gritty elements, we would say that you just raise the modulus to the power, and then you take the argument times the power. So just to put this into practice for you, it says use DeMoivre's theorem to find the following complex number power. It says if z is this number 3 CIS 40, or 3 cosine I sine 40 degrees, then we want to go find z to the 6th power. So to find z to the 6th power, let's start with this. Z to the 6th power would be the same thing as 3 cosine I sine, let me get that out of there, cosine I sine 40 degrees, and we are raising this now to the 6th power. So if we're going to raise this to the 6th power, DeMoivre's theorem just states that all you have to do is you have to take now this modulus to that power. So we take 3 to the 6th, and then we say take it times CIS 40 degrees also times this 6. Okay. So we end up with this right here. We say 3 to the 6th power. This is something that I may want to check here. I think it's 729. We say 3 power 6. Nope. 3 to the power of 6. I guess that makes sense. Yeah, 3 times 3 is 9. 9 times 9 is 81. 81 times 9. No, this is 729. So why am I not getting this here? Sorry. So we say 3 the power of 6, maybe it's that one there. Ah, there it is. Okay, so we get 729. Sorry for the delay there. 729 CIS 240 degrees. Okay, and so then this is also something that if we had to sketch it out, we would say that all this is saying is that we're going in a 240 degree direction. This is the argument of our vector here. So we say theta is 240 degrees. And just to represent this here, we would say, oops, just to represent this here, let's do this. That's what I meant to type in. We'd say that this r value right here would have to be 729, which is really far away from the origin, but essentially that would be our complex number right there. Okay, we can make our triangle out of it. So now what I want to do is I want to use DeMoivre's theorem again, but let's say we started in standard form, and let's weigh the benefits of doing it with DeMoivre's in trig form. So we say if z is some complex number so that it's equal to 1 plus I, or 1 plus 1I, this is some complex number in x plus yi, or standard form. So if we were to raise now z to the 10th power, you have to understand that we'd actually have to take 1 plus I also to the 10th power, which means we would actually not be able to distribute this straight through, but we would have to take 1 plus I times 1 plus I times 1 plus I times ... Let me put that down here. ... times 1 plus I. But we'd have to have 10 factors of this, and I want you to imagine how long does it take you to do this just by foiling 2 of these out. So if we had to do this with all of them, all 10 of these factors, it wouldn't be very desirable. So what we're going to do is we're actually going to rewrite this in trig form first. Okay, so just like any time you rewrite a number in trig form, the first thing to do is graph it. So we say 1 comma 1 would be our point. So over 1, up 1, this is our complex number in standard form, and there is our vector right there. So here's the deal. We say that this is the point 1 comma 1. That's our x and our y respectively for this x plus yi number. What we want to do is we want to find 2 things about this if we know these are 1. We want to find the argument, so we want to find this theta right here, and we also want to find the modulus, or the absolute value of this, so this r value. So we're going to find both of these, starting with r. R is always the easier of the 2 to find. We say that it's always the square root of x squared plus y squared, where x and y are both 1 respectively. So we say r is the square root of 1 plus 1, or in other words, r is the square root of 2. So we're just going to keep this number here. It's exact. We don't want a decimal, so we want exact values. Furthermore, we could say that we know that the theta hat, or the reference angle for our thing here, is the tangent inverse of y over x. And so we say 1 over 1. Again, we could just get out a calculator here. I think that this would have to be a 45-degree angle reasonably here, but we say 1 divided by 1 if we're going to do tangent inverse on this, it certainly does say that our theta hat at least is 45 degrees. So if that's 45 degrees, then this theta here, what would it be? Well, in this case, it would have to be 45 degrees also. Okay, and we also found out that r was root 2. So at least we could say this. We say that the number z, let me rewrite it this way. The number z in trig form would be this. We'd say that its modulus was the square root of 2, and we have CIS times its theta, and its argument in this case was 45 degrees. In other words, this number that we graphed up here is just the square root of 2 units away from the origin in a 45-degree direction. So that being said, let's again try to take z to the 10th power. In this case, it becomes a lot easier. As a matter of fact, we say root 2 CIS 45 degrees to the 10th power. So in this instance, what we're going to get is this, and I'm going to carry this down over here. We get the square root of 2 to the 10th power times cosine I sine of 45 degrees times 10. So we end up with this. And actually, I'll re-express this as root 2 squared to the 5th, which is to the 10th. The only reason I say this is because the square root of 2 squared is just 2. So we get 2 to the 5th, and 2 to the 5th is 32. We also get CIS 450 degrees. Now, here's the interesting thing about this answer right here. Although it is technically accurate, we tend to only want to allow our angles or our arguments to be somewhere between 0 and 360 degrees. So if this is a 450 degree angle, of course 450 degrees would be all the way around once and then 90 more degrees. It would be this thing right here. So we'd say theta is 450 degrees, and we are going out in this direction, and according to this we say r is equal to 32 units. The idea I want to present though is this. We should always use some angle between 0 and 360, or we say it's the smallest possible angle. So if you get 32 CIS 450 for an answer, the better way to write this is 32 CIS 90 degrees, because 90 is both between 0 and 360, but also the smallest possible angle that gets me from the positive x-axis to my vector.